Hey guys, welcome to the Biomechanics 1 video series. This is the second video looking at the impulse-momentum relationship. This one is specifically focused on the impulse component. There are several aspects to this particular video that we'll be discussing. One is just to again quickly review where the impulse portion of the impulse momentum tends to come from, its applications and how we tend to calculate it, and under what situations does it become quite useful for us as analysts with regards to forces. So the first one, in a previous video we derived the impulse momentum relationship from Newton's second law equation, force is equal to mass times acceleration. In essence what that looks at is if I have some particular object of a given mass and I have a force that is acting on that particular object, that the specific object that that force is acting on will undergo some kind of acceleration, right? Now this force may act on this object for a specific period of time, which we'll just call delta t, right? Some final time minus some initial time. And as a consequence, this object will undergo some change in momentum, right? So this object has mass and its velocity which will change, which is where this acceleration component tends to come from. Okay, so we know that this acceleration or this momentum is proportional to this force, right? We've already derived that formula and said that this component over here, this force times this change in time, is called the impulse. And that impulse will cause some change in momentum. And what we can see is that this change in momentum is proportional to this impulse, right? So the bigger the force, the greater the change in momentum will be. So if the force doubles, the momentum will double. The change in time also tends to affect it. So as this change in time is greater, the momentum will tend to be greater. If this is shorter, then the momentum will tend to be shorter. So that becomes quite useful for various applications. So we will look at the fact that oftentimes you may want to investigate the force of a jump. In other words, how much force does the person have to generate in order to reach a certain height? How does that change? How does the force tend to change as a result of fatigue, for example? What are the impact forces of landing? So if I land from various heights and I try and minimize the force of landing, how do I go about doing that, and is that strategy effective or not compared to some other strategy? What about concussion forces? So if you look at boxing sports or martial arts, oftentimes you'll have some kind of impact force with the head that tends to act for a certain period of time, which may or may not result in concussion, and there's specific studies that look at that in a lot more detail. Also games like rugby, for example, since athletes are undergoing tackle situations, they may experience a concussive force, and we can investigate that further. What about impact forces between various objects, right? So I've given some examples here. I may have a impact force between a golf club and a golf ball. In this case, I want to increase the impulse between these two objects, and you'll realize as we go along that there's various factors that govern that. One of them is the material that these two objects are made up of, but in many respects it's a contact time and force application problem, right? So how do I magnify the magnitude of these forces? In other instances, I may want to minimize the force. So you can see here that in an impact situation where a car impacts with a wall and this individual would experience large changes in momentum, and there may be a collision between this individual and the car, I have very, very large forces acting in a very, very short period of time. I may want to develop something that increases the time over which those forces tend to act, right? So in this case, the development of an airbag, although it cannot reduce the overall forces that are experienced, it can increase the time over which those forces act, and that therefore decreases the force of impact between this individual and the car. In various running shoe developments, you can see here that there's quite a thick heel pad, and that tends to increase time of impact between your body weight being slowed down relative to the ground reaction forces that are being generated, right? So the thicker this heel is, the less force you will tend to feel at the heel. And there's various arguments for and against whether that's a good thing or a bad thing, and that's another story for another time. What about force on various anatomical landmarks? So we use quite sophisticated foot scan technology. So we have this in the lab, and that can look at not only force but also impulse on various anatomical landmarks, specifically medial lateral heels, midfoot, your metatarsals, your 5 metatarsal areas, and your toes. So how large those forces are and how long they tend to act for gives me an indication of impulse and how I can modify that, right? Is it a good thing? Is it a bad thing? And should I or should I not modify it, right? Oftentimes, what we can do with the sophisticated technology is to use things such as force plates or foot scans in order to find out what the magnitude of the forces are and how long they tend to act for. So what that allows us to do is to plot force versus time graphs, and then thereby calculate what the impulse forces are. The impulse forces are defined as the area underneath a force time graph, right? Oftentimes that's very, very difficult to do. Like I said, you need very sophisticated equipment to do that, but there are ways of approximating what these forces are, right? In this case, I may be interested in what the maximum force is, but I might not necessarily be able to calculate that. I can, however, calculate the impulse and give an indication of what the average force application is over a specific time period. There may be changes in force, right? So I have some kind of positive impulse and some negative impulse, and that can tell me the change in impulse, right? So area underneath the graph tells me what the impulse tends to be. So I'm going to get a worked example just to get you guys a little bit more comfortable with what the implications of that are. Let me just go up a little bit here. Alright, so say for example, I have a force versus time graph. And with what most of you guys will be dealing with is constant forces, right? Where the force does not change much. So let me just draw a straight line here. So say for example, I have this scenario where I have an unchanging force, a constant force of, and we'll say that that is 250 newtons, acting for a period of 0.5 seconds. So we say that's the area underneath this graph that tells me what the impulse is, right? So if I can calculate all of this, then I'll be able to identify what the impulse is. So in this case, we know that impulse is defined as the force acting times the change in time over which that force tends to act. We know that area, it depends on what the shape of the object is, but this is a rectangle, and that's simply the base multiplied by the height, right? So you'll notice that the base is this change in time, which is just 0.5 seconds, and the height is just that constant force that tends to act at 250 newtons throughout, so it's just 250. And that gives me 125 Newton seconds. Cool. What about if I deal with a force time graph that looks something somewhat different? So something that I guess is in many respects maybe a little bit more common, and may look something like this, that I have an increase in force and a decrease in force. In this case, what you'll notice is the force is changing constantly over time. Well, not constantly, it's just changing over time. Let's say it's acting over that same time period of 0.5 seconds. This peak is reached at exactly the halfway mark, which is 0.25. And again, this peak here is F max. Okay. So now your job is to calculate the area underneath this graph to find out what the impulse is, right? So how do we go about doing that? Okay, so I've got two triangles that are similar, exactly the same shape. Let's say this half is what we'll calculate first, and then we'll calculate the second half over here. Now these two triangles are the same, so you'll see that the calculations will be very, very similar. So again, area in this case of a triangle is half of base times height. So I'll call this A1 and I'll call this A2. So the area of A1 is equal to 1/2. The base is 0.25. And the height is, oh sorry, I didn't put that in, as F max is also the same that we, not the same, it's just 500 newtons. Okay, so that's 500, and that's going to give me 62.5 Newton seconds. We'll get into why that is the case just now. Area number 2 is also half of base times height, which is the same as the previous one, which is also 62.5. And that means if I add both of them together, I'll get the area underneath this whole triangle, which is going to be 125 Newton seconds, which gives us quite an interesting correlation between these two, right? So you can see that the area under this triangle, under this rectangle, is the same as the area under this triangle. That's done purposefully, because what you'll find is that when I have a changing force over time, that will be equal to the average force acting over that same time, right? So if I can get this average force, which is a constant force, and I calculate this area, it will be the exact same as the area underneath this triangle where the forces are changing, right? It makes our mathematics a lot easier, and we don't need the same sophisticated equipment as we do to calculate this F max. And you'll see that these two areas are equivalent, right? So if this is 250 and it's acting over this 0.5 seconds, I get this 125 Newton seconds. And that's exactly the same as the 125 Newton seconds that I get here. Okay, so the impulse is going to be the exact same, although the maximum forces are going to be different. Here I have an average force of 250, here I have a maximum force at some point in time of 500. But that's beyond, that's more than enough for what we need at this present point in time. Something that I just want to unpack is just the dimensions of impulse. So impulse is denoted by this letter J, and that's, like we said, equal to this force times this change in time. So from a dimensional analysis point of view, what are the SI units of impulse? And I've kind of already alluded to that just now. It's basically the SI units of force and time, right? So we know that force is measured in newtons and time is measured in seconds. So the SI for impulse is Newton seconds. What you'll notice though as well is that newtons are defined as kilogram meters per second squared, right? And if I multiply that by a second, one of these seconds cancels out and I'm left with kilogram meters per second, which coincidentally is the same units as momentum. Okay, it's one of the reasons why they are equivalent. Okay, I think that's all for this introduction to what impulse is and what its applications are, right? In the next video, we'll work through a couple of examples and start looking at how can we use this relationship between impulse and momentum that we see over here in order to make some really useful inferences and applied examples with regards to biomechanics. Alright, that's it for now. Thanks for listening.